Bismillahirrahmanirrahim. I'm Amal Sohail and my roll number is 21PE04. Today I'll be implementing Lab 3 of Digital Signal Processing, which is about representation of unit impulse, unit step, and exponentials, and making signals out of deltas. The objective of this lab is the representation of unit impulse function and unit step function, making unit step function using unit impulse sequence, and making any arbitrary signal out of deltas. Here is the task 1 of Dsp Lab 3, which is about plotting unit impulse sequence in MATLAB. This code defines a function that generates an impulse sequence with a single non-zero value, an impulse at a specified index n0, which is 0, within a specified range of indices n1 to n2. Now by calling the function, we can observe the output. Here we can see the unit impulse sequence both in continuous and discrete plotting methods. Now here is another code from which we can visualize the scaled, reflected, and shifted variants of the unit impulse sequence in continuous and discrete plots. Let us observe the output. Here we can see the unit impulse sequence in continuous and discrete subplots. This graph represents the scaled version of the unit impulse sequence as its index is multiplied by 2. So this function is increased by the factor of 2. The reflected variant represents the total opposite of the original signal, and the shifted variant represents that the signal is shifted to the value of 2, both in continuous and discrete plots. Here is the task 2 of Dsp Lab 3, which is about plotting unit step sequence in MATLAB. In this code, the function takes 3 inputs n0, n1, and n2, which are the starting and the ending indexes of the unit step sequence. Then it generates the step sequence x by checking if each index in n is greater than or equal to n0. If an index satisfies this condition, the corresponding element in x is set to 1, otherwise it is set to 0. In the calling section, the plot and stem commands are used to generate step sequence both in continuous and discrete formats. The axis function is used to set the limits of the axis for better visualization. Now let us observe the output. Here we can see both the subplots of the continuous and discrete form of the unit step sequence. Now to observe the shifted, scaled, and reflected variants of the unit step sequence, here is the provided code. Let us run this code. We can see the 8 subplots representing the original unit step sequence in continuous format and the original unit step sequence in discrete format, and there are different operations applied on the signal, which are scaling, reflection, and shifting. The signal is scaled by the factor of 2. So that the expansion occurs in the signal. The reflected variant is totally the opposite of the original signal, and the signal unit step signal is shifted to -3 because of the factor -3. Task 3 of the lab is about the construction of unit step signal by adding shifted impulse sequences. The code clears the workspace, initializes sequence indices n from -5 to 5, and then creates an empty vector u to represent the step sequence. The code uses the for loop that iterates through indices k from 0 to 10, then generates an impulse sequence x starting from the index k, and then it adds to the unit step sequence u. Visualizes each impulse sequence x in the first subplot. After constructing the step sequence u, it plots it in the second subplot. The axis limits are set to ensure clear visualization. Now we will run the output. Here we can see the code dynamically builds a step sequence by summing individual impulse sequences and visualizes the process using subplots. Task 4 of the lab is about creating arbitrary signals by using unit impulse sequences. This MATLAB code demonstrates the convolution operation between three given input sequences x1, x2, and x3 and a unit impulse sequence impulse. An input sequence impulse is created as a binary vector where the value is 1 only at index 0 and 0 elsewhere. Three input sequences x1, x2, and x3 are defined with specific values. A range of time indexes n is defined from -20 to 20. Then convolution is performed between each input sequence and an impulse sequence using conv function. The same option ensures that the output sequence has the same length as the input sequence. The results of the convolutions y1, y2, and y3 are plotted in separate subplots using stem. Each subplot represents the convolution of one input sequence and with the unit impulse sequence. Titles, labels, and X's are represented for the clear visualization of the graphs. Let us see the output. Overall, this code illustrates how to compute and visualize the convolution of discrete time signals with a unit impulse sequence, offering insights into how the input sequences are affected by the convolution process. Task 5 of the lab is about splitting a signal into its even and odd components. This MATLAB function even odd decomposes a real signal x into its even xe and odd xo parts. The function starts with a check to ensure that the input signal x is a real sequence or not. If it has any non-zero imaginary components, it throws an error indicating that x is not a real sequence. It calculates the time indices m by taking the negative of the flipped n array. Then it determines the common range of indices m and n by finding the maximum and minimum values between m and n, and finally it sets up the time indices m to span the common range. It aligns the input signal x with respect to the time indices m. It calculates the shift nm required to align n with m and then shifts the input signal x accordingly. The aligned signal x is used to calculate the even part xe and odd part xo of the original signal. The even part of the signal is computed as the average of the aligned signal x and its time reversed version. The odd part of the signal is computed as half the difference between the aligned signal and its time reversed version. Now, in the calling section, this MATLAB script decomposes a given signal x into its even and odd components using even-odd function that we have declared in the previous script. It then visualizes the original signal alongside its even and odd parts in three subplots. Let us run the output. Here we can observe that the first subplot displays the original signal x plotted against time indices n using a red stem plot. The second subplot shows the even part xe against its corresponding time indices m in blue. Similarly, the third subplot illustrates the odd part xo against its time indices m in green. Each subplot is titled accordingly to indicate the type of signal being visualized. Like the first one indicates the original signal, the second subplot represents the even signal, whereas the third subplot represents the odd signal. Overall, the script provides a concise demonstration of signal decomposition into even and odd components, followed by clear visualization for each component. Here is the last task of Dsp Lab 3, which generates and visualizes a continuous time signal and its discretized version using an impulse train. The vector t defines the time vector from 0 to 2 seconds with a sampling interval of 0.005 seconds. Then it specifies the frequency of the continuous time signal, which is equals to 1 Hz. It generates the continuous time sinusoidal signal, CT signal, by the use of cosine function with angular frequency f2 pi t. Now for the discretization with impulse train, it sets the sampling frequency fs to 10. Then calculates the sampling period ts as the inverse of the sampling frequency. Then it creates an impulse train by the variable impulse underscore train is equal to 0, 1 length of t corresponding to the sampling period ts. These intervals are marked with ones. Obtains the discretized signal by multiplying the continuous time signal with the impulse train. Now let us observe the output. The code plots the continuous time signal in the upper subplot using plot command. It adds the titles and labels to the upper subplot for clarity. Then it plots the discrete signal in the lower subplot using stem representing each sample with a discrete marker. Then it adds a title and labels to the lower subplot to identify the discretized signal and its characteristics in the time domain. In summary, this script illustrates the process of discretizing a continuous time signal using an impulse train and provides visualizations of both the continuous time and discretized signals for comparison. Thank you so much for watching. See you in the next video. Allah Hafiz.